I've had a fantastic, I've got it easy with Nancy's talk, Peter's talk, Gerald's talk, Kevin's talk. So I think all the background kind of has been set. And in this talk, I will focus on applications mainly. So I will talk about specific physical systems, microscopic Hamiltonians, and kind of what we can do using these process tensor techniques. Does that work, by the way? Is that loud enough in the back? Okay, great. So before I get started, I should thank the people who really did the work, and that's mostly my postdoc Moritz here, and also almost all of it, pretty much anything that's relevant to this meeting is done in very close collaboration with Jonathan Keeling and Brendan Lovett. Okay, so I said I was going to talk about specific physical systems. I'm taking a leaf out of Alex Chin's book, and I'm going to introduce kind of two kind of model systems which we've used to benchmark and study the techniques. The first one here is a semiconductor self-assembled quantum dot. So this is an island of a sort of lower band gap semiconductor embedded in a higher band gap substrate. Let's grow. They comprise about several thousands, maybe 10,000 atoms, and it's like a particle in a box. And it's a sort of nice model system where you can have, you've got the particle in a box, and you can have a ground state where there's kind of nothing there really, and then you can excite a single electron-hole pair. And it's not a Frenkel exciton; they're not so strongly Coulomb bound, but they are confined to the quantum dot. And you can excite that by shining a laser on the quantum dot. So there's a strong optical transition dipole moment, which allows you to control this two-level system. It also means you have an interaction with the electromagnetic environment. You can have spontaneous emission, you could put the thing in a cavity, etc. So those things are interesting for single photon sources and other things. So the effective Hamiltonian here is really, we've got the ground state, we have the excited state, and we can apply a coherent laser to drive Rabi oscillations, do that sort of stuff. We've also got, in addition to the optical environment, we have coupling to a vibrational environment, and there we write that in the sort of usual spin boson form. We say when we're in the excited state, the charge configuration dot is different, kind of all the ion lattice sides get displaced, and we have a displacement of our bath of oscillators. So we just have a quasi-continuum of oscillator modes, and this is the interaction Hamiltonian. I've not written down the electromagnetic one. Yes, Tom?
Sorry, could I just clarify what are the two levels? What are the two states?
The two states is the quantum dot in the ground state. There's no kind of, electron in the conduction band of this quantum dot, right? You can go and promote an electron from the valence band to the conduction band. You leave a hole behind. You've got this bound electron hole pair on the quantum dot. That's the excited state. So it's kind of, obviously it's a complicated kind of many atom system, but it has a it behaves to a very, very good approximation as this two-level system for reasons we understand from first principles. Okay, so this is a quantum dot. Why am I showing you it? Because it has, I guess, it's pretty rich toy model to play with, and you can do that. It's experimentally relevant as well. This is old work where we derived the Lindblad-Master equation really to kind of, when you shine a laser on the quantum dot, resonant with the transition frequency, you get your Rabi oscillations. And in this case, we didn't do it as a function of time, but we changed the pulse area, we changed the laser intensity, and you get some damping on these oscillations. And then the damping becomes more severe at higher temperature. So this is actually well captured by a Markovian master equation. You're driving it strongly. The coupling to the vibration is relatively weak. So the master equation kind of works, and we get good agreement between theory and experiment. In a different regime, though, that's both for kind of relatively weak driving as well as strong driving. If you look at the emission spectrum, if you look at the photons of the photoluminescence from the quantum dot, if you drive it, you can't use that weak coupling master equation. What the theory shows you, which is the sort of orange curves here, is a polaron transformed master equation. And that says the master equation still works, but you need to polaron transform, and you're sort of making the assumption the coupling to the bath is dominant. That works well for this. In the general case, it doesn't either. And what we've looked at here is a situation where you're trying to excite this quantum dot using two laser pulses with different frequencies, none of them resonant with a transition frequency. And that idea was really taken from a different paper where said, wouldn't it be great if you can kind of create an excitation in the quantum dot that will give you a single photon? You don't have any laser photons at that frequency. So it's kind of easy to filter that out and be sure you only have that single photon in the system. Turns out, in the absence of a phonon environment, that doesn't actually really work. You sort of see the phonon sideband here. It does work once you're out the phonon environment, but you probably actually want to use different intensities. In some sense, this kind of suggestive here, you couple with kind of different strength to the quantum dot at different sides of the zero phonon line. And then we can kind of map out what happens if you change the laser intensity versus the kind of, how much is blue, how much is red. And you can create this excitation map where we care about the state of the system, and neither of these two master equations is adequate. And actually this map was calculated using POPI, path integral calculations. This is what gave us this map, but the point is you need something that enables you to kind of sometimes interpolate between these two master equations and be more generally valid and capture the dynamics of the system. Yes.
So what's the spectral density?
The spectral density in this case, so that is a deformation potential coupling. It's a super ohmic at low frequency, and it comes with an exponential cutoff. We usually use a sort of Gaussian cutoff. The cutoff depends on the wave function of the electron and the hole. They're isotropic and the same size. It's just a simple sort of Gaussian cutoff. The super ohmic, that's from the coupling to the deformation potential. So we know what the spectral density looks like. It's relatively simple compared to molecular systems, sort of single peak of, I think I'll show it on some future slides. Okay, that's the first model system. I'm probably spending too much time on these, but here's another one, because Olivier talked about kind of transport across molecules. So here's another, this is two kind of this is two graphene kind of leads in the molecule. Stuck between them is a porphyrin molecule with suitable kind of linkers. This is obviously a schematic depiction, but that's something where my collaborators in Oxford, they did that in the lab. This year's a few years, 5 years ago, we derived a master equation to describe the charge transport or the kind of current you get across such a molecular junction if you apply a bias between these two graphene leads. Crucially, you also need to have a kind of handle to tune the molecular orbital. And what we were interested in is resonant tunneling. So we've got the two Fermi energies and we've got one molecular orbital, and we kind of wanted to, with a gate voltage, kind of plunge that and keep it in the bias window. If you don't do that, you get co-tunneling and you get sort of different behavior. But in the resonant tunneling regime, you need a gate generally. So, and what we did, I'm not showing you the equation, I'm kind of showing you the process we went through. We started with a polaron transformation because we thought actually the porphyrin molecule, when you put additional charge in, it's going to change shape. And so there's kind of a strong coupling to the vibrational modes, if you like. So we started with the polaron transformation. Then we derived in that frame a second order master equation. We did something to have a self-consistent Born approximation. And those kind of two things mean it wasn't just a box standard Lindblad master equation. It kind of had more stuff go into it. And what it gave us is something which I'm not showing you. We called it generalized quantum master equation. And we were kind of pleased that we could recover various kind of well-known limits. So that was kind of a nice piece of theory work. Does one need it? Yes, one does. If you take such a molecule and you have a junction, you stick it in a fridge, and you kind of apply a bias voltage and tune your gate voltage, you can look at how much current you get through it. So this is changing the bias and sort of seeing how much current flows through it. That's when we're in the resonant tunneling regime. And you kind of see if we don't have anything, we don't have vibrations, we don't have an environment, we don't get the right answer. Certainly don't get anything that matches the data. what we actually found in this case is we needed one particular vibrational mode associated with the porphyrin molecule and a sort of broad background, probably due to the solvent and kind of as a general environment. And that gave us the good fit here, and it also kind of works well for the differential conductance. And you can look at these Coulomb diamonds, as they're called, where you change the gate voltage and the bias voltage. And yes, there's some sort of there's some artifacts in the measured data, but generally speaking, theory and experiment kind of work. So this did require, I don't think I'm going to talk about these plots, but what this did require is a relatively sophisticated master equation with some sort of fancy stuff going in. We did make a lot of approximations. We were kind of pleased it worked in the end. It is limited to weak molecule lead coupling. So we can't, so we're kind of deep in the sequential tunneling regime. We don't get much throughput. And it would be nice to relax some of these assumptions and have a different technique, a different tool, which allows you to do that in a more assumption-free way. Won't talk about this, but we applied the same model, different molecule, different experiment in Delft, but sort of similar ideas. And again, the kind of the master equation worked. So what we want is something where we get the dynamics of an open quantum system in a numerically exact sort of converged way, in the same way that Nancy started yesterday. So long introduction, but that's what we want to do. And we've got a quantum system of interest, and it has a few levels, not necessarily two. And there's an environment around it. We've got some possibly bosonic degrees of freedom. It could be the vibrations. We've possibly got fermionic degrees of freedom. That could be the metallic leads. We may have spins. We've not actually done much with that, but we may well have spins. We say in principle, what we'd need to do is solve the Schrödinger equation for the whole thing. And of course, we know we can't because the Hilbert space is too large. So direct integration is impossible. And the aim of the game, pretty much anything we've done is, or all open quantum systems in some senses, to find a numerically tractable description where we have the system and we somehow capture the influence of the environment in a compressed way that we can represent and compute. Down here, this is really just a process kind of tensor depiction. I'll move to the next slide. So I'll tell you how we get to this kind of process tensor description, how we get this compressed environment in a way that's different compared to the way that Peter talked about yesterday for tempo. So with that introduction, so we've got a system, we've got an environment. What we do, and that's been done in all the work here as well, is we discretize time, introduce different time steps with time increments delta t, and then our process tensor, we sort of this is what I call the process tensor, or in this case, call it an influence function up here. This encapsulates what the environment does to our system at kind of different points in time. It has a capability to kind of carry forward information and capture non-Markovian effects. I'll tell you how we construct that, I think, on the next slide. But this kind of sort of way of thinking about it, and calling it the process tensor, I guess, is a convergence of the tempo algorithm and some of the work done by Kavan and Felix, and actually Jürgensen and Pollock came up with what I call PT tempo. But what we end up with is an efficient way to compress this, write this influence function matrix product operator form and compress it and make it tractable. So how does, also Kavan talked about this, I won't go into that, but you can get the process tensor in different ways is the point. So here's how we do it in the automatic compression of environment approach. Our starting point is an explicit microscopic Hamiltonian. We've got a system Hamiltonian, and we have an environment which we must be able to represent as a sum over smaller environmental degrees of freedom, smaller modes of the environment. So I call them, I label them with the index K. So we discretize the environment. Sometimes we have a discrete environment to start with. In this case, we want a discrete environment. In any case, even if it's a quasi-continuum, we want to approximate it by a discrete set of environmental degrees of freedom. what these HEs are, they're the environment, the free environment Hamiltonian, and the interaction term of that environmental degree of freedom with the system. And the only requirement we have really is that these individual environmental modes are small enough such that we can solve them efficiently, at least numerically, kind of one by one. We want to be able to write down the Liouvillean for environmental degree of freedom K, or mode K. We can write down this Liouvillean. We've got the time evolution, the propagator for this. And with that, I'm going to appeal to what Kavan just did. He said we kind of take a crayon, we write down our trotterized time evolution, and I've already got two here, but we sort of take a crayon and we kind of color in the bit that's due to the environment. We separate that out from the M, which gives us the free system evolution, and we call that the process tensor of a single environmental mode. So the Q here is maybe a single environmental mode. And now I've got another one. I'm doing this again for a second environmental mode. That gives me the P. And then all I need to do, and this is where I won't be showing you the details, there's some subtleties involved in that. But all I need to do is to combine these two process tensors, Q and P, to create a sort of single one. I need to combine them and I need to compress them. And if I don't compress them using singular value decomposition, I'm still solving the whole thing. I haven't done anything except trotterized. Right? But this is the kind of trick, is to build this up one environmental degree of freedom at a time, iteratively. And as long as you can combine two process tensors and then do a compression sweep, you end up with something which is a PT MPO. Yes, Kavan.
So the assumption is that the environmental degrees of freedom are not talking to each other.
They're not talking to each other. They need to be independent, and you need to be able to independently solve them. That's true for the split boson model, where you just think of them as different harmonic oscillators, but they don't need to be harmonic oscillators. There could be fermions, there could be spins. We've not made any assumption about the form of the interaction, but the system can sort of only interact with one kind of mode, kind of in a pairwise fashion at a time, right?
What is Q again? I am sorry.
Q here, what is this Q or that Q? Sorry, they're two different Q. So, well, here's the sort of, I've combined Q and P and I called it Q again. So this is bad notation on my part. But Q,
that's the next letter.
Yes, maybe. So this is bad notation. Q is a single, up here, Q is a process tensor due to a single environmental degree of freedom. But really all I've done is taken the crayon that kind of Kavan took, and I've sort of drawn a line around all the bits to do with the interaction terms and the environment propagation, kind of in a trotterized picture.
P, right?
So is P. It's a different degree of
Oh,
freedom. P is a different degree of freedom, and then you combine them together and you compress. And that gives you what maybe I should be calling Q here. We call it Q because we call it Q in the paper all the time. So I need to work on the notation here.
The separate interfunctionals for the different.
Yes. One degree of freedom at a time. Yes. So this is two, and then we kind of merge it, combine it, compress it, and then it's kind of rinse and repeat. You keep doing that. That's the idea. And if you keep doing that, it's probably bad to see it, but I couldn't resist trying to use the sort of artistic depiction of it. You keep doing that. Oh, this is the colors don't work. But we kind of think of a different environmental modes. K, we sort of have this different rows here, and we kind of do this iteratively, one mode at a time. We create a process tensor for that mode. We merge it with what we already have. We do singular value compression, and we add the next mode. And we kind of keep doing that, and we end up with these sort of Christmas tree-like structures. And that's the way to build a process tensor. And that's really all I want to say about it. Now I'll show you what we can do with it. And I'll focus in particular on some things which might be a little bit harder if you're doing, if you're using a different approach.
Can I
Yes, sure.
So if I understand correctly, all right, you define them as the different interfunctional factors for the different paths of freedom. But if you are now, I think you're trying to represent this in MPS form.
Yeah.
But when you do this for one degree of freedom, the memory is going to be infinitely long. So how do you compress this thing for one degree of freedom?
So we don't directly control, we don't truncate the memory, we don't control the memory. We've kind of trotterized the time evolution, we write it in the sort of tensor network form. The memory is represented by how much kind of bond dimension we have. So this is related to Kavan. It's kind of, if you go back here, it's, so the kind of how much, yes, the bond dimension between adjacent queues, kind of that sort of tells us something about the non-Markovian memory. So in a scenario where we have a very long memory time, the bond dimensions will be high and we are not able to kind of compress it further. If we have a single mode, we can't compress by itself, we can't compress it at all. So we can't compress it for single mode, but once we've merged a few, the compression starts to work. So, and the compression often in this sort of spin boson type problem, it gets more effective the more modes you add. So it's a more non-Markovian system if the memory is finite and small.
That's exactly what I'm asking. So
Yeah.
when you start this,
Yes.
you're going to have, with the first mode, infinitely long memory. So how can you then start this and
So
get the matrix all the way to
we have connected, our queues are connected across the entire length of the code. That's okay, right? With the first mode, we don't need to compress it in that sense. Gerald, you want?
Yeah, I just want to maybe help clarifying that if you just have a single spin, for example, in environment, your bond dimension, even though you have infinite correlation, your bond dimension will still be 4 at most because it will
The bond dimension remains small, right?
So there's no problem.
Yeah.
So in the space of the path, I thought you are compressing the system. Oh, you're not capturing the system yet.
No.
Okay, I see.
No. The system is external to the process tensor here, and maybe that's a good point to make. Right, what we call the process tensor here is maybe a bit different from the one Kavan had. Kavan had his initial system density matrix and environment density matrix as part of this comb, and then the unitary evolution or the kind of evolution of the system as well. For us, this is sort of separate. This is only the environment and the interaction of the system with the environment. So the system Hamiltonian is kind of, that's the M's here, and the initial state is not specified. So this is, yes.
So is this then similar to what Garner Chan had a paper about compressing maintenance functional, writing in MPS form and compressing it?
I'm not sure. I don't know. Yeah. We can discuss later. So let me show you what you can do with it. So this is a small application, but of something that's the resonant level model for those who know it. We've got a system here, a site, it could be empty or occupied, and we've sort of got two sites which are the leads or the environment next to it, and we have a coherent coupling G. And of course, we can solve that as a closed system. It's kind of really just 3 two-level systems. We can find an analytical solution for it, and that gives us this sort of sine squared behavior as a function of time for the occupation of the site. So that we can work out. We can also work that out using this ACE algorithm, but the compression hasn't taken place. This is an incompressible at this point. The memory length is infinite. It's infinitely non-Markovian. You can't throw anything away. You kind of can't compress, but the computer code we wrote to do that can solve it. Right? It's infinitely non-Markovian, but it's included in what we can do. Now we can come and we can kind of change the setup slightly by adding more environmental modes here. And in that case, we see if we start with 100, if we go to a large number, we kind of get a nice sort of exponential saturation of the, so that becomes Markovian, essentially. We start occupying our site over time in an exponential fashion. And if we have 10, that kind of, we could do perturbative expansion. We see we have a quadratic behavior at first. If we have 4, we still get kind of oscillations. We only show part of it. But the kind of point here is the approach, depending how many environmental modes you add, you can go from something which is essentially infinitely non-Markovian to something which is completely Markovian, and we're using exactly the same computer code, kind of other parameters. So we're kind of, the approach is capable of sort of spanning very different behaviors. Yeah.
Why does it become completely Markovian? I mean,
Sorry?
Why does it become completely Markovian?
If you make the environment sufficiently large, you kind of end up with a Markovian limit here, right?
I don't understand.
You don't understand, yes.
I mean, Laplace functional for spin boson for harmonic.
This is not spin boson. This is essentially lots of two-level systems, and we call it kind of charge transport fermionic modes. This is not a spin boson model.
The environment is
The environment is two-level systems,
but
effectively.
why would that become Markovian again?
So
It can be mapped on a harmonic path.
why does that? So I think what we, yes, but I need to think about that. But so intuitively, we have more fermionic leads in the environment, all coupled to a single site, which is initially empty, right? We kind of think what we expect to happen is for that level to occupy and stay occupied. But yes, let's talk about that later. Okay?
Erik, each of these modes that you have for the reservoir, do you have them coupled to their own Lindblad reservoir? Is it just a unitary system?
No, it's overall it's a closed system. They're all independent. They're all independent. Each coupled. Each of these coupled to S.
Yeah.
Yeah.
It's a chain mapping configuration, basically. You're replacing the environment by a chain. Yeah. But in the diagram that you have there, you have it as a star, so you have it in the energy basis. Each of the modes in your reservoir there couples to your system. It's a chain mapping what you're doing. Do you know?
I don't know.
Yeah.
Chain, it's just a bunch of levels.
It's a bunch, yeah.
So there is actually a
descriptions.
The record result.
Chain mapping and a star configuration as it has there, they're equivalent descriptions. Just rotated by a unitary transformation.
Harmonic one to a different spectral density. That's a very good result, and we can prove it in linear response theory and all.
Okay, I'll be interested in looking at that. So let me move on. We could talk about it in the break. Let me move on and talk about other things you can do. So one thing we haven't done, we've not exploited a particular, we've just said we break the environment down into many different degrees of freedom. And it doesn't need to be a single environment. We can have different types of environmental degrees of freedom, which couple to our system in different ways, right? So what that allows us to do, for example, is to look at multiple environments in a very, very easy way. And this is taking the example of the quantum dot I showed initially. I think I had a 0 and an X here, so this is a ground state, an excited state. We can apply a time-dependent Gaussian excitation pulse, that's our laser pulse. We can detune that laser pulse, this is blue detuned, and then we can sort of see what happens if we include the coupling to the phonon environment or we exclude the coupling to the phonon environment, and we can also include or omit a coupling to the electromagnetic environment and allow for spontaneous decay. So if we don't, and what I'm showing you here is a table. We've got phonons, photons, and we treat them in different ways. We kind of use QAPI here as a benchmark because we know that works well for the system. The photons we use either as Lindblad, not at all, or using or ACE, and we're looking at different combinations. So if we don't have phonons present, we can not fully excite the system because we're detuned. We're blue detuned. A detuned laser pulse will not lead to a complete inversion of the population. This is kind of just this dashed line, right? It doesn't really matter that we have the photon decay. by the time the laser pulse finishes, we're back in the ground state.
So can I clarify here?
Yes.
Are there photons as explicit harmonic degrees of freedom, or is it just?
It's a quantum optical master equation. So we use it as a Lindblad master equation. Believe that. So you can derive that using electromagnetic modes as explicit degrees of freedom. Yes.
But it's not just a time dependent field that you're writing here on the left.
There's a time-dependent field. We do have spontaneous decay. So that manifests as a Lindblad operator, as a lowering operator going from X to G.
So that's what you're treating, not a Hamiltonian augmented by a time-dependent driving term.
No. So we've got the time-dependent driving term as part of a system Hamiltonian. That's a coherent laser pulse we apply to the quantum dot. Yes. And then in addition, we give ourselves a Lindblad operator, which describes the decay. Both of them couple kind of via the transition, the optical transition operator. So if we're detuned, we don't have phonons, we kind of we don't reach full inversion. If we do give ourselves phonons and we're blue detuned, we kind of know we can excite via the phonon sideband, and we can reach a higher level of excitation. And this is what you see. It doesn't kind of matter how you do the phonons, really, whether you treat them using ACE or using QAPI. As soon as you add the phonons, you're going to create more inversion in this two-level system because you can go via the phonon sideband. So the detuning doesn't hurt you to the same amount. What you do see, and then here's where you see the spontaneous emission, here's where you see the radiative recombination of the excitation. And that, whether you model that using a Lindblad operator, which you kind of just add in operationally or phenomenologically, or whether you actually, in this case, Nancy, here, where it's ACE and ACE, we do treat the electromagnetic environments as a bunch of harmonic oscillators. The second environment, it couples via sigma X, not via sigma Z, to the two-level system. We can do that. We get the same result as from the Lindblad decay. Because we know the Lindblad decay is the Born-Markov approximation is very valid for the spontaneous emission in the quantum optical master equation. So that's not unexpected, but it's a nice check to be able to do that and treat both types of environment kind of in the numerical formulas. This is the point of the upper panel. In the lower one, so I think we kind of took that as success. We recover kind of known results really. Although we've solved an easier problem in a more complicated way, where we do ACE for both environments. Yeah.
But it's also, it looks like Lindblad is the same as QAPI, even for the phonons.
For the phonons, hang on, the phonons we don't treat with a Lindblad operator, right? The phonons we treat with QAPI, ACE, or not at all. Okay. Yeah. So the phonons, we know we can't treat with a Lindblad operator because we don't get the phonon sideband excitation if we use a Lindblad operator. The phonons need to be treated on a more rigorously. The radiative recombination, Lindblad's fine, that's the point. So, yes?
Very dumb question.
Yeah.
What's the goal here? Like, so are you trying to match QAPI or?
Well, we're trying to benchmark our. Right one, so I want to convince you that ACE works, and I want to convince you by showing you examples where we know the result, kind of benchmarking against techniques which are reliable. So
I guess the question is dumber than that for me. Which one is the right or accepted result? Let's call it on the top plot. Is it the QAPI Lindblad would be the thing that...
There's nothing wrong with QAPI Lindblad. You would expect that QAPI Lindblad works well. QAPI converges for the phonons. There is maybe the question you have once you add in the phonon environment, the photon environment, is there anything that's non-additive between the two? Because the photon Lindblad term you've derived making a Born-Markov approximation in the absence, in some sense, of the phonon environment. So that's second order perturbative. The radiative decay doesn't know anything about the phonons. Whether or not that's a good approximation, right? You might have a question mark there. I guess this line suggests it's fine. Okay, but Yes.
Sorry, why don't you show copy with copy?
We didn't do it, right? In this case, we did not do quappy and quappy. Yeah. So, right. So, okay. Let me try and move on. Let's see how far I get with this talk. I probably won't get to the end by the coffee break. Okay, so here what we're showing here is we've got our quantum dot initially in the excited state. And now we give ourselves a structured photonic environment. Imagine we're in a cavity or on a photonic crystal with a certain bandwidth. And then we look at two different cases. We have a relatively large bandwidth of the photonic environment, but it's no longer kind of completely, doesn't have a flat spectral density, which so we take a large bandwidth and a small bandwidth case. In the large bandwidth case, and here the time-dependent driving pulse is gone, but we start off excited and we just really want to see the radiative decay. We want to see how the system relaxes back to the ground state. So if we have a large bandwidth electromagnetic environment and whether we include the phonons or not, doesn't really matter. We get exponential decay from a Lindblad term. So here we've got phonons with quappy, we've got the photons with Lindblad. This gives us exponential decay. The kind of phonons don't really do anything. We can not do the phonons, use ACE for the decay, we get the same line. We can use ACE for both environments. Everything sits on that exponential decay. So what this shows us that radiative recombination doesn't care about it shows us two things. It doesn't care about the phonons at all. And the photon decay is well described by Lindblad term. And Nancy, we could have done the photons with quappy and we would expect exactly the same result, right? The Lindblad operator is fine for the spontaneous emission. So that's the kind of point here. That is, if your bandwidth is sufficiently large. If you make it smaller, in that case, you do see deviations between the phonons being present or not present. And that's kind of these two lines. That's the orange line and the red dashed line. So in this case, the presence of the phonons modifies the radiative relaxation of the quantum dot. So we have what we might call a non-additive effect between having this quantum dot embedded in two environments at the same time. Does that make sense? Yeah.
I do have a question, but I should let you
finish. So, and I'm not saying I am not saying you couldn't have embedded your system in two environments at the same time using a different approach. What I am saying is it's particularly easy with the way ACE is set up because we don't really care about the form of the spectral density. We don't really care about the fact that your environment interacts differently. We just need more. We just have more discrete environmental degrees of freedom to kind of represent these two environments. Something else we can do, because I said all we need to be able to do is take our environmental degrees of freedom and write down a Liouvillean for them. So far, we were talking about the free constant evolution for the environment degrees of freedom, but actually, with the Liouvillean, we can introduce Lindblad processes onto the environment. I think Peter said yesterday, it's easy with kind of tempo. You can add additional Markovian Lindblad processes to the system. In this case, we can easily add Lindblad processes, dissipation, equilibration, thermalization to environmental degrees of freedom. This is not now derived from a microscopic interaction Hamilton, but something we know might be happening. And we can go further. We can use time-dependent control of environmental degrees of freedom. We can introduce a time-dependent driving on an environmental mode. So what this is showing, this example here, we've got a driven two-level system again, like a quantum dot with a resonant laser. And that interacts with a multi-mode cavity. We've got different cavity modes. They're all leaky. They all have loss out of the cavity. And at different points, actually in this at 4, here I only show 2, at different points we come in and we shine a little bit of light into the cavity and we start populating one of these cavity modes. We can do that in a time-dependent way at different times, and we can track what the system does, or the excited state of the system as a function of time. Where there's nothing in it, you just get your full Rabi oscillations. Once you start to put photons into these cavity modes, these are the sort of the durations of the pulses, putting photons in the cavity modes, you see the dynamics change. And you can, I'm not showing the plots, you can kind of take that apart. If you do that instantaneously, you kind of see, you see more clear, without loss, you see the frequency changes. There's a dispersive kind of coupling here. You see the Rabi frequency changes. So you can, so I think this sort of showcases how we exploit the fact that all we need to write down is Liouvilleans for the environmental degrees of freedom. And that gives us the ability to kind of control the environment and the system via the environment. Okay, let me show you a couple more examples. How am I doing for time? I've probably used most of it. Huh? 5 minutes, okay, that's not good. So I should, maybe I'll skip over this I won't talk about this then. This is something where we used 2 quantum dots undergoing cooperative emission, and we kind of look at 2 quantum dots, each with their individual photon bath, but kind of emitting photons collectively, inspired by experimental results. Let me do a quick wrap up and then give you a very brief outlook in the last 5 minutes. So what this automatic compression of environment enables us to do, it's a technique to get numerically converged dynamics. As we trotterize, we have a singular value threshold. We discretize our environment if it's continuous. So the number of environmental modes and how we sample that is important. It works with any form of interaction. It's not limited to rank 1. We can do James-Cummings, dispersive coupling, nonlinear couplings. We can do it for any environment which we can break down in chunks. I've said that before, just shown you an example where we said we can have a dissipative in a sort of Markovian way environment, time-dependently driven, etc. It doesn't need to be Gaussian, it could be non-Gaussian, and it's very easy to combine different types of environments. So I think I would say it's easy to use. What we kind of put in is really, once we've done the environmental discretization and we specify the Hamiltonian, that goes in, our convergence parameters goes in. In practice, that can be a challenge to find them, but conceptually it's simple. And we have our system Hamiltonian, system initial state, they're separate. They're not required for constructing the process tensor. They come afterwards for the final contraction. That gives us our time-dependent evolution of the density matrix. And we have that available as open source. We're hoping to integrate into OccupyC. I'll keep talking for a couple more minutes until Jonathan shuts me off, because there's more stuff I wanted to say. Key limitations, performance can be an issue. As large systems, Gerald showed us a way. This was not ACE, but it's a PT-MPO technique, so that we had that yesterday. Long times, many time steps, and maybe I'll very briefly show you something here. Again, this isn't quite ACE. This is going back to the Jurgensen-Pollock influence functional, or PT-MPO, which is constructed differently. This is something we have a preprint on. There's also more recent work from Walter Strunz's group, and Dom and Dom have something in preparation dealing with kind of infinite times. And a big limitation is the environmental modes cannot interact, so it can't deal with highly correlated environments. The sort of divide and conquer, this is a preprint. This is the kind of triangular tensor network which Peter showed us yesterday, constructed in a slightly different way, in the Jurgen-Pollockson way, where these bonds become time local. But what you see on close, what you may see on close inspection is there's blocks here which are self-similar, which are redundant. And what that enables you to do is to kind of use these blocks and recycle them. And then you can use a divide and conquer scheme, and it gives you, even if you don't have any memory truncation, gives you a massively improved scaling in the number of SVDs you need to do the contraction. with a cutoff, it turns into something that's the number of times you need for the cutoff times log n, which is the number of time steps. And then you can go even further and you can kind of come up with a repeating unit, which again, just by graphical inspection here, you kind of see we have this block. We've got the green block, and we can use that to construct a repeating unit, and that enables us to, in this case, the number of SVDs no longer depends on the number of time steps you want to propagate. You still need to do the final contraction. What does that enable you to do? We've got again our driven quantum dot, our old friend, two-level system, ground state, excited state with a coherent laser driving, gives you the dressed states, and in the absence of phonons, you would expect to see a monotriplet. But now we've got the coupling to photons. Here's the question: what does the spectral density look like? It's a super-obic Gaussian cutoff. And we can work that out for different types of driving strength here. And we kind of see our 3 peaks, but we also see on a log scale, we see deviations from the case with no phonons. In order to get these spectra, we needed about 1 million time steps, because we look at a 2-time correlation function, we Fourier transform it for the spectrum. We have a multi-scale time problem where photon and phonons have different correlation times. We drive our system strongly. We kind of need to resolve the fast dynamics to kind of get the slow dynamics. So that required 1 million time steps. And if you think about how long does that take, sequential is Jürgens and Pollock. So this is an improvement on the original tempo. But this shows you the scaling, the computation time as a number of time steps. With our divide and conquer, we can do millions of time steps in minutes. So in practice, that's just recognizing that redundancy, the self-similarity, gives you a massive advantage. We can also go to larger things, look at super radiance. I'm out of time, so I won't talk about that. Outlook, because Peter talked about it and Alex talked about kind of looking from the environment, and Kavan mentioned it. What do the bond dimensions mean? What can we do? This is actually using ACE. We can kind of understand what the compression is and what the compression. So this is constructing 2 Q matrices, kind of here, a single block here. And if we construct that mode by mode, and we can kind of think of the compression as a lossy rank reducing transformation, which we have available in matrix product operator form. We can compute a pseudo inverse, and what enables us to go back to the full environment Liouville operator and actually say something about bath operators or system bath combined kind of observables. So we don't necessarily get them all right, but we have a way of asking the question, asking the process tensor the question kind of, what can you tell me about a bath observable? And if we do that, and maybe I won't explain it, but we've done more work to kind of get closer to this kind of molecule between 2 fermionic leads, where we give ourselves fermionic leads, charge transport, and now we can look at not just the occupation of the molecule, but we can get the current. And this is kind of really asking kind of what's the exchange of charges with the environment. There are some subtleties here. That's very much work in progress. I think I'm over time, so I should again highlight Moritz, who did all the hard work. And it's just an overview of the stuff we do in my group. So thanks a lot.
We have a lot of questions inside wake. I have time for a few more questions, but I think that others might need to go to coffee. So if you have maybe different questions from ones before, yes, but otherwise that might go to coffee.
I had a follow-up question to the ones before.
Okay.
It's a quick one though. So in your back to those calculations with the photons and phonons.
Yes.
So typically spontaneous emission is much slower than decay from phonons. So I wonder why you're saying that the phonons don't have an effect in the case.
They don't. So the rate for spontaneous emission is much slower. Yes, you get the quantum dots have a lifetime of about a nanosecond. Kind of phonon processes happen on a picosecond, but the rate of radiative recombination of spontaneous emission is not affected by the presence of phonons. If you create a superposition state in your quantum dot where you have a superposition of ground and excited state, then what the phonons will do, they will lead on a picosecond timescale to decoherence of these two, but it doesn't change the populations. And the rate of spontaneous emission in that case, if your photon environment is fully Markovian, so you have a flat spectral density, only depends on the population of the excited level. That changes when you give yourself a structured electromagnetic environment, as I showed with a reduced bandwidth. In that case, that's no longer true. And Paul is dying to chime in.
And I just a question relates to that. So what if you took a system with, say, a discrete phonon mode and relatively strong coupling, so something where you get a clear phonon plus photon emission?
Yes.
With that, I mean, that seems like that must change the decay rate because you've got two ways to decay.
So, yes. So there's a slide I'm glad I removed. I had something on a 2-bath tempo paper, PRX Quantum from last year that Peter was also involved in, and work led by Dom Gribben and Dom Rouse. So you can, if you sort of think of sort of Frank-Condon shift, absolutely. If you have a strongly coupled single mode, right, you can kind of think of your shifted parabolas and then draw a diagram, and you see that you do get non-additive effects, and you can even get a single two-level system if it's at high optical temperature, relatively weak photon coupling, strong vibrational coupling to reach population inversion. So in that case, you certainly get a rich interplay between the two things. In the normal quantum dot scenario emission into free space, it doesn't matter. What people do, of course, they put them into photonic waveguides because they want to use them single photon sources. There you have a structured electromagnetic environment. And then, as I showed, you start to see non-additive effects. They're relatively mild in this case, though. But yes, you can certainly think about different regimes where that matters.